Here's the guide for factoring polynomials. We need to start with the common monomial factoring. Then whatever will be the result, we're going to categorize them as to whether the result is a binomial, trinomial, or multinomial, and we have specific processes under specific results. Then we end it. Let's factor completely x to the power of 6 minus 1. This example is specifically given because this is a very unique one. We can actually attack the factoring of this in two different ways. We're talking about the use of two different methods, as this given example fits the conditions for both. Take note, we have here binomial expression. Take note that we have a lot of process for binomial expression. We have difference of two squares, we have difference of two cubes, we have the sum of two cubes, or even the use of common monomial factoring. But since here we cannot find any term that can be factored for both using common monomial factoring, so we are going to stick with those binomial expressions. And take note that the operation separating them is subtraction, so we can actually look into the possibility of this being a difference of two squares or a difference of two cubes. Which would you think fits the condition? Take note that for difference of two squares, let's say here, difference of two squares, okay, it should be that the two terms should be perfect square. And then in identification of the squared expression or squared term, we need to look at whether the numerical coefficient are perfect square. We have here 1 and we have here 1, right? And then the literal coefficient are also perfect square. Take note that the exponent of our x here is even. Automatically, that's a perfect square expression because x to the power of 6 is the square, okay, is the square, sorry, of x cubed. So this is the difference of two squares. Now, how about difference of two cubes? Is it possible? Take note, for a difference of two cubes, we need to make sure that the terms are expressed as both perfect cube. Now, -1 or -1 or even 1 is a perfect cube. 1 here is also a perfect cube. And the exponent of our x is divisible by 3. Hence, it's also a difference of two cubes. So you can attack it passing through difference of two squares first and then proceeding into a difference of two cubes, or you can start with a difference of two cubes first. For me, it's easier for me to look at the possibility of using difference of two squares because once I guarantee that it is a perfect square, a difference of two squares, then I have a binomial, two binomial factors, right? Only binomial factors of opposite signs, okay? But for difference of two cubes, we actually have a binomial expression and a trinomial expression here. So nevertheless, if you're going to use both of them, you will get the same result. Let us try to show probably both of them, but I will start with difference of two squares, okay? The difference of two squares allow us to factor this again in a binomial, two binomial expressions where the operations are opposite, but they will have the same first term and the same second terms. The difference of two squares, we only take the square root of the first term, x to the power of 6. Pardon if we are using radical expression, but this means we are actually dividing 6, the exponent of x, by the index of this one here, square root, meaning 2. So we are having here x cubed. Okay, that's the square root of the first term. Now the square root of the last term, disregarding the sign because that becomes the operations here, square root of 1 is just equal to 1. In short, the terms here are x cubed plus 1 and x cubed minus 1. Okay? So again, x cubed plus 1 and x cubed minus 1. Now, looking into this is why this example is very unique and I might use a lot of spaces at the bottom. You have seen here, by the way, if you're not convinced with that, use FOIL method. X cubed times x cubed is x to the power of 6. This is positive x cubed that's minus x cubed, so they neutralize one another. 1 times negative 1 is minus 1, so it's correct. The thing here next is that both of these binomial expressions actually fits the second one rather is a difference of 2 cubed, because x cubed is a perfect cube and then 1 as mentioned is a perfect cube. But this second here is also sum of 2 cubes. That would mean we are to further factor them using specific factoring for each. Take note that for each of them, we will be having a binomial expression and a trinomial expression. In short here, and pardon again for this very lengthy process, for the first one, you will have a binomial and trinomial. For the second one, you also have a binomial and a trinomial expression. Okay? So I'll be showing you the two methods I presented earlier, or mentioned rather earlier, and it's up to you which you will be using. Now, for the factor of, we know this is a perfect cube because the exponent is 3, divisible by 3 in here as well. So the factor for this, if you can still remember, square root of the first term is x. Square root of the last term is 1, using the sign plus here. That's for its binomial expression. For this, let me jump here if it's okay with you. Same process, square root of the first term is x. Square root of the last term is 1, and using the sign here, minus. Okay? But the trinomial expressions are dependent on your binomial factors. Okay? That's very clear in the previous examples discussed in this playlist. Now let's look into the first part here. The trinomial expression, square the first term, x squared. Please try to review the previous two videos for you to be guided in this process. The square of the second term becomes the third term plus 1, and the middle term is the product of them. X times 1 is x, but negative of it, or the opposite. So x times 1 is x, opposite of positive x is minus x. This is now, or these are now the factors of your first binomial expression, which is just a sum of 2 cubes. Now for the second, again, similarly, square the first term. Your trinomial expression is dependent on your expression here. Square the second term. The square of negative 1 is positive 1. And then you multiply them. X times negative 1 is negative x. And the opposite of that is plus x. Similar here, x times 1 is positive x. Opposite is minus. So x times negative 1 is negative x, opposite is positive x. So basically these are now the factors if you're asked to factor completely. This is the result when we stop the first with the use of difference of 2 squares before the difference of 2 cubes. Now, what if we start with a difference of 2 cubes? So in the application of difference of 2 cubes, we'll be patterning that here. But take note that this is just, the x to the power of 6 is the square of x cubed, or you could also write this as the cube of x squared. In short, the cube root of x to the power of 6, 6 divided by 3 is x squared, right? We're using that because if you have your x to the power of 6 minus 1, and you would like to pass through this first and see if the result here is the same as later, so you will have here the first factor, which is a binomial term in a trinomial expression. Okay, so the cube root of the first term is x squared. Okay, the cube root of the second term is negative 1, so you will have x squared minus 1. But for the trinomial expression, the square of the first term, x to the power of 4, the square of the last term, you will have here plus 1, and then when you multiply them, okay, when you try to multiply them, x squared times 1, negative 1 rather, is negative x squared, and the opposite of that, or the negative of negative x squared, is positive x squared. Okay, so you can see they are very different, but when you look at this expression here, this is now a difference of 2 squares, which will follow two binomial expressions of opposite sign. So you will have here two binomial expressions of opposite sign, yet your trinomial expression is still x to the power of 4 plus x squared, and have here plus 1, right? So x squared, x to the power of 4 plus x squared plus 1. So we have here this expression, the square root of the first term. Now we are now using difference of two squares. Take note, this was the result using difference of two cubes, but since this is a difference of two squares, so we will have it this form here. Square root of the first term, x, is x. You have here x as well. You will have square root of 1 is 1, and you have here 1, and then you are just going to have the opposite signs. You would notice that x plus 1 is here, and rather here and here as well. X minus 1 is also here and here. But why is it that this is the other form, and then the other one you have these two forms here at the top? Can we get the same result if we try to multiply them? By the way, we may not factor this anymore, okay? Because it is a trinomial expression that will not fit any of those forms. Because if we talk about perfect square trinomial, this should have here 2 for that to be a perfect square trinomial. For a general quadratic trinomial, your a here is 1 and your c here is 1. So AC method is 1. The factors of 1, okay, when added will result to 1 is not possible, right? Because if you have here 1 and 1, negative 1, negative 1, when you add them, you will not get positive 1 here. This is already okay. But I would like to show you here the result for these two, this one here, this one, and this, which will result to this form as well. Let me extend some space here at the bottom. Okay, sorry for that. Okay, so let us use some of the spaces or additional spaces. Pardon for this. Let me add again spaces for further illustration of equivalence, okay, of both. So you have here, sorry for that. Okay. So if I'm going to multiply x squared minus x plus 1, let us see when we multiply it to x squared plus x plus 1, if this will result to the trinomial expression here using the second method, x to the power of 4 plus x squared plus 1. By the way, we are doing this so that you would appreciate the two methods, and it's now up to you which is easier for you. Definitely, the first one might look easier, but you need the concept of difference of two squares, difference of two cubes, and sum of two cubes in order for you to guarantee your factors. The second one still uses sum of two cubes, difference of two cubes, and then later on difference of two squares, but we have different results. So we are just going to multiply them if possible. So first term to first term, okay, x squared times x squared, x to the power of 4. X squared times x is plus x cubed. X squared times 1 is plus x squared. Next, negative x times x squared is minus x cubed. Negative x times x is minus x squared, and negative x times 1 is minus x. That last term, 1 times x squared is plus x squared, 1 times x is plus x, and 1 times 1 is plus 1. So x to the power of 4 stays as it is. Okay, the x cubed and this one would be simplified. X squared minus this is simplified, but you also have another x squared here, so you have plus x squared. You'll have minus x plus x, they are now cancelled, and you are left with the remaining term plus 1. As you can see, the product of those two trinomial expressions using the first method is just equal to the lone trinomial expression in the second method. This guarantees that whichever you attack this type of problem, whether you factor them using difference of two squares and see if there are items that can be factored using difference or sum of two cubes, or you start with difference of two cubes, then later on factor possibilities for difference of two squares, you will get the same result. It's just that they are actually transformed or written differently because they can no longer be factored once we reach at this point. So hopefully this example is clear. We'll have another example that will allow us to use multi-step, but with using the concept of difference of two cubes or sum of two cubes or a combination of all of those processes in the next one. The next factor we're looking for is for our next subscriber. Subscribe now!